Welcome to the Cosmic Pie Podcast, episode 30, season number 4. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
We are broadcasting live from the campus of the University of North Dakota here in, Robert, look at my merch, Grand Forks. You see that hat?
Ah, yes.
Where are we at, Robert? Where are we at, in case you needed a reminder?
Well, I think we're at the University of North Dakota in Grand Forks, North Dakota. So
Now, we do have a live chat feature that's running that Robert will be keeping an eye on. So if you have any comments or questions that you'd like to ask throughout the podcast, feel free to send them our way. Now, one of the things we like to do at the beginning, of course, Robert, is you're famous for this now, I would imagine.
I don't know about famous or if I should be famous for that, but we got our disclaimer, and that is that the opinions that Wayne and I express are those of ourselves. They do not in any way reflect the University of North Dakota, the state of North Dakota, College of Arts and Sciences, Department of Physics and Astrophysics. Just us. You got to come at us, folks.
Now, please remember that we are broadcasting live if you're hearing us now on YouTube, as you know, but we also upload our podcast the very next day to Spotify. So if you'd rather go on that sort of platform and watch us, then feel free to do that.
Absolutely.
And most important, because it affects our motivation in doing this podcast, is to know that people, A, are watching it, B, that they like the podcast. Imagine if no one liked it. You had no viewers or nothing. That would be that would get to you after a while. I think you'd stop doing the podcast, right, Robert?
Let's face it, we've discussed that in the past. So, yeah.
So the more viewers, the better. So don't forget to give us that beautiful thumbs up. Subscribe if you haven't subscribed. And we'll see that, and it makes us happy, right? Good thoughts. Now,
absolutely.
One of the things we're going to talk about, starting the whole thing off, is something that's coming up this week, Robert. So we would be remiss if we didn't mention that, and that's the partial lunar eclipse. Now, this coming Thursday into Friday, so that would be roughly 2 weeks then, essentially, after the solar eclipse that people we're looking at over in Europe and in Greenland and Iceland. So 2 weeks after the new moon is the full moon's phase. And because the alignment is close again, right, that the moon's orbital path is intersecting the Earth-Sun orbital path, that you're going to have a lunar eclipse. It's not a perfect alignment. So as you see here in this slide, the moon will not be fully blocked, but the Earth's darkest part of its shadow, the umbra, as we learn wouldn't you learn that like in kindergarten physics?
Something like, actually, I don't remember. I've known for a long time that it was the umbra and penumbra.
Certainly got to be in elementary school somewhere, right? We
Yeah.
learn that kind of stuff. And so it's almost totally blocked. Not quite. It's like roughly 96% of the moon will be in the Earth's darkest part of its shadow. But this is an event that's also viewable from here, from Grand Forks, and in a large chunk this side of the Earth. And you can see a map down below in that slide to show you where it's visible. So if you're listening and you're in Australia, or if you're in India or in China or in a good chunk of Russia, you're not going to be able to see the eclipse at all. But if you're in...
I got to admit, this is one thing that I do like about lunar eclipse over solar eclipse. Do not get me wrong. Solar eclipses are spectacular. But with a solar eclipse, you've got to be in the right place at the right time. With a lunar eclipse, half the world gets to see it. Yeah. So to me, they're actually kind of nicer. You've definitely got a bigger chance of seeing one.
And you know the lunar eclipse is a lot cheaper to view on average than a solar eclipse. And you know why, right?
Do what? Sorry?
The lunar eclipse is a lot cheaper to watch on average than a solar eclipse. And you know why?
Because it's cooler at night? I don't know.
No, I said a lot cheaper. It's because typically you're going to have to fly somewhere around the world to go see a solar eclipse, and there's usually expensive. Yes. Here's an example of that. So the next full, total solar eclipse is going to be in August of 27, so next August. That path of totality goes through Gibraltar, across the Mediterranean, right? Part of Africa, including Egypt, for example, and down in the Arabian Peninsula, Yemen, and those areas, places you probably don't want to go, right? You got to be very careful. They're not always friendly everywhere around the world, as we all know.
Yep.
And you have to go there. Well, that costs a lot of money. And then, of course, a lot of times people that offer, for example, hotels or Airbnbs and so on, they know the eclipse is happening, that they're in that prime location, a relatively small area. And so what do they end up doing, right? Capitalist 101.
Yep.
They charge you a lot of money for these rooms, way more than what typically would be. So if you add that all together, I mean, that's a lot of money to go see one of these eclipses.
Yep. Well, what burns me is that actually a lot of them aren't aware that the eclipse is coming. And then starting about a year, when people start buzzing about it, they find out, and they actually then start canceling people's reservations for that time frame, doubling or tripling the price, and then opening back the reservations. And it's like, no, sorry, that's not right. Start keeping up with things.
Yeah, and
you signed a contract and reserve this room for this person. You don't get to cancel it and say, "Oh, we didn't know." Too bad. So sad.
And we had a member of our department that actually happened to him. He booked, I won't say who it is, but he booked a room way ahead of time. Mm-hmm. And then a few months prior to when the solar eclipses take place, they canceled his reservation and opened up the room for like several times what he paid for.
Right.
And he actually had to threaten to sue them before they reversed their decision and gave his room back for the actual price that he had initially signed up for, reserved the room for.
Right. And it's like, no, it should have never been a question. They should have just, oh, dang, we missed out. But here we go.
Here we go. Well, at least for the lunar eclipse from this side of the world, it doesn't cost anything. Hopefully the weather cooperates. And I think for us it's supposed to, if I'm not mistaken.
Yeah.
Supposed to
Thursday looks pretty good.
Yeah, Thursday evening. So for us here in Grand Forks, that the sort of the heart of the eclipse will be at about 11:12 p.m. Not too late. A lot of times these things are 3 in the morning, and a lot of people can't stay up that late because they got to go to work early next day. But this one's not so bad at 11:12, and that'll be where the largest part of the moon will be or its darkest part of its shadow. So that will be kind of cool. So I'm sure.
Oh, dang.
What's that?
Well, I'm just noticing the altitude. The limits out at the observatory I'm the telescope operator for. The horizon limit is 30 degrees.
Oh, you missed it by 5.
And I'm looking at 25.09 and going, oh, man, I was going to take images of this thing.
We have to tear the side of the observatory off so we can lower the telescope down further.
Right? Just tear out the wall.
Put it back when you're done.
Yeah.
That's what staples are for, right?
I'm sure the director will be fine with that.
Oh, wow. So be it. Anyways, at least we don't have to fork out $3,000 or something to go see this thing on Thursday night.
Absolutely.
Now, some places it happens, like the middle of it will be technically Friday morning. So watch out for that. This event is Thursday evening. Okay.
That's it.
And then the next thing that's coming up, and this is on Sunday, and this is early in the morning for some of us. This is the launch, at least it's scheduled for this time, of the Nancy Grace Roman Space Telescope. We talked about that in the past. Due to be launched this Sunday at 6:26 a.m. our time. And this was a Falcon Heavy rocket, so we'll see how all of this plays out. I'm not sure of the weather right now for launch time. And as far as I know, it's the Kennedy Space Center. But hopefully it all, mornings are usually good. It's usually later in the afternoon this time of the year where you get the thunderstorms build in, and that can cause a delay.
Believe me, growing up on the Gulf Coast, it's usually about 3 or 4 o'clock. You can set your watch by the thunderstorms that blow in.
Yeah.
As everything starts to cool down a bit, the humidity got up from evaporation to 100%, starts cooling down. Here comes a major thunderstorm. It's a daily thing.
Do you remember from your history what rocket was hit by lightning in the Apollo days?
I do not.
That was Apollo 12.
Oh.
So they launched in rain, and as it got roughly a minute into flight, it generated its own lightning discharge. And
I'm not surprised.
And then the power in the command module all went off because of that. the guidance computer that's running the Saturn V rocket was not in that location, was in a different part of the rocket. That was unaffected by the lightning, thankfully.
Well, that's fortuitous.
Yeah. And so there's a famous line where mission control, like when it happened, they had a few seconds to do something. The display was all messed up when it came back up, tried to come back up. So is there like the famous call that was done by mission control for one of the flight controllers was SCX to aux. So secondary control to auxiliary. And it was one of these calls that they never used in simulation. It was this obscure thing that they never, ever dreamed of when they're doing the, trying to mess up the crew so that they don't know the switches to throw in different emergencies when they're simulating all this stuff on the ground. And this was something that they never, ever experienced. And some of the astronauts, you can hear them talking, saying, SCX to aux, what the heck is that? Right? What does that even mean? And that was the call. One of the astronauts did that, switched it to auxiliary, and then eventually they went back to the SEC again, and that fixed the display. Everything came back up. And why that's important is the rocket itself was okay. There was no danger of that going off course or something. But you want to go to the moon. So as soon as you get in Earth orbit, the first thing you start doing is checking all the systems to make sure you're ready for the translunar injection, the burn that takes you onto the moon. If there's something wrong and it's critical, then the flight is canceled and you probably come back after a few orbits and not get to go to the moon.
There you go.
So in that sense, that switch saved their mission, right? That they were able to go to the moon and actually land on the moon. Yeah. And the other thing that's neat about Apollo 12, Robert, so this is the second flight, right? Apollo 11 is the one that they landed on the moon for the first time in '69, July. So Apollo 12, I believe it went in November, if I'm not mistaken, of that same year, '69. And we don't have a lot of footage of lunar activity, the EVAs on the lunar surface. And the reason for that is because one of the astronauts mistakenly pointed the camera at the sun like relatively soon after the EVA.
Oh, no.
Yeah, relatively soon after the EVA began, the moonwalk, and burnt the camera out. So there's no...
I was about to say, those old transistors and everything just got totally cooked.
Yeah, there's really no good footage of them walking around on the moon. There are lots of photographs, of course, that were processed after they returned, but live feed from the moon was nothing on that day, right? So the networks, as my understanding, had to scramble and do like a mock simulation inside the studio or something where they had some stuff, right, to show this is what they're doing now would look like this if we could see them live with the camera. And in fact, it's an interesting story. Some people have speculated that this whole moon hoax, that we never been to the moon, it was all done in the studio, is they were referring to what they did during the Apollo 12 mission, where they were simulating this in the studio, the television studios, because there was no live camera feed.
That makes sense. Sorry, that makes complete and total sense. The problem is I can't see that footage looking anything like the Apollo 11 or Apollo 14, because of course 13 didn't get to land on the moon. So, yeah.
Yeah, you could easily I've seen some of the footage, right? You can go to YouTube and look at coverage of the Apollo 12 mission and see it. And you can tell it's simulation. In fact, they have words simulation. They told people it was.
Of course.
But anyways.
But at the same time, I will sit there and say, War of the Worlds, sir.
Right.
War of the Worlds.
Touche.
Breaking in every 15 minutes saying this is a radio program. And yet people were still calling in, talking about how they were seeing the aliens attacking and shooting at water towers and everything else. People don't pay attention sometimes.
Now, the Nancy Grace Roman Space Telescope, first of all, it's named after Nancy Grace Roman, who was really the first astronomer that worked for NASA. And she became chief of, astrophysics and a big player within NASA itself. The other thing is, it's an interesting here to this object, this telescope. It was donated to NASA by the National Reconnaissance Office several years ago. In fact, there was two of them. And what they were using it for, it should be obvious. They were having, similar telescopes in Earth orbit. Of course, they're not pointed out in space. They're pointed down here on the Earth If you like,
Now, why would they do that?
yeah, if you like to spy on people. But so when the NRO gave these telescopes to NASA, NASA's like, oh, what am I going to do with these? And to do anything with them, you had to outfit them, you had to refurbish them, you had to put in new instrumentation and all of the sort of support structure you need to, beam down the signals from the telescope and then send up signals up to the telescopes, and they need all that, power sources, all this stuff. And then, of course, you need to pay money to launch the thing.
Yep.
But these telescopes, are similar in size in terms of the mirror to the Hubble Space Telescope, so they're about 2.5 meters in diameter. Now, the way they were built, the reason they were built that way is I think they were initially designed because they were going to go up on space shuttles themselves and fly out of Vandenberg, which was supposed to be the second shuttle launch facility, that the military was going to send up launches of the shuttle exclusively for them. So that would keep, praying eyes away from them a little better, and you wouldn't have live coverage on television like you had for most of the other shuttle flights. That kind of all fell apart, mostly after Challenger, and then certainly after, Columbia was done, right? They weren't going to do this. So the money they put into the shuttle launch pad out in California was, in some sense, a wasted money. So they had to get rid of all that. And when they did shuttle launches for the military, they just followed the launch up to a certain point in time, after it got into orbit, and then they immediately shut the camera feeds off. Nobody could see anything, and they blacked out everything from mission control, because you don't want to show anything like what's in the cargo bay, right? When you open up the cargo bay doors, because then that's the military satellites or equipment or whatever they have. It's all top secret. So that was the end of your coverage, until the shuttle landed. Essentially, you weren't going to really see anything else. Now, for these type of telescopes, even though they have a mirror that's similar, it's not of the same curvature. So it has a much different focal length, as we say, right? The distance from the center of the mirror, basically the center point, to where the light of an object would be in focus, from infinity. And the optics that it has, the main mirror, actually gives rise to a field of view. So what you can actually see in a single image with a camera when you hook up a detector is actually 100 times greater than the Hubble Space Telescope.
Right.
It's not quite the same comparison. It's almost like looking down a straw and then looking around with one eye, what you see in terms of area.
Right. This is a survey telescope.
Oh, for sure, 100%. In fact, that's what it's designed to do, right? You put a science case forward. Okay, we didn't have money earmarked for this thing to begin with because it was kind of dropped in our laps. So we have to go back to Congress and say, could you divvy up some money? Can you cough up some money to build the structure, the detectors, and everything else that you need, and also, of course, pay for the launch service? Could you do all of that? And they're going to say, well, why should I? You have the Hubble Space Telescope. Well, wait a minute, right? The field of view is 100 times greater than the Hubble, which means in a single exposure, we're going to see 100 times the area than you get a single exposure with the Hubble. So we can use this telescope to do large area surveys, and we can pick up objects that normally are very, let's say, not very numerous, very rare, that if you survey a large enough area, you might be able to find these type of things.
There we go.
And so that was the selling point in all of that. And the other thing is, of course, you're putting modern detectors on the telescope. And Robert, from experience, that the detectors that are recent are more sensitive than the detectors that are, 5, 10, 15 years old.
Absolutely.
And when the sensitivity is greater, you're going to see a lot fainter. So even though you have the same size mirror, then you're going to do a lot better in terms of gathering light and actually recording it on an image or on a spectrum or whatever, because of the sensitivity of the detectors is so much greater. So there are a lot of advantages to this telescope. And if you know a little bit about astronomy and the detectors, then it's not hard to sell you that this should be launched, that this is a viable instrument and could make a lot of interesting discoveries even though we have other telescopes that are in space like the Hubble Space Telescope.
Absolutely. It's a different type of astronomy. It's a different type of work. Sure, you can grab a screwdriver and drive a nail with it, but it's much better with a hammer, you know. Or I guess a better analogy would be you're going to be able to put up walls with a framing hammer faster than you can with a finishing hammer. So that's kind of what we're working at here. It's similar tools, but they're designed and crafted to do different things.
Yeah, for sure. So that's going to be interesting. That's coming up, as I said again, as you see there, then this Sunday morning. So hopefully it goes off without a hitch. These rocket launches, you never, ever know what's going to happen. And I don't mean weather delays or mechanical delays. I mean, as soon as it starts, you could have a catastrophic sort of problem that occurs, and that would be a tragedy. You lose the whole thing at 30 seconds into launch or something.
Oh, yeah.
So we've had stuff happen in the past, so yeah.
Yeah.
The other thing to update people on is what actually happened to Starship, flight number 13. So when we last were sort of at this story, the ship itself had landed in the Indian Ocean, and it's watertight, and it was floating. It didn't do a hard crash like I think all of the other ships that landed on the water, right, broke apart and sunk within a few minutes probably. So this one here actually stayed afloat. It has enough, buoyancy, and it's airtight that it could do that. And when it stayed afloat for a few days, that allowed SpaceX, who launched the thing, to get detailed views with it, usually with a drone, that they could look at the surface of the tiles and see what type of reentry damage was done and what they need to do to make things even better the next time and so on. So they did all kinds of detailed analysis, and when they were done, it was like, well, the thing is still like floating, right? At this point, it's almost like a navigational hazard for ships that are in the ocean. So it's like, what do we do with this thing? So they decided, it might be worthwhile to analyze it directly. And so let's see if we can tow it somewhere and get it into port and get it out of the ocean. So that's what they decided to do. So SpaceX probably contracted a ship that was large enough to be able to do this thing. And they got to the ship and put flotation devices around to help stabilize it. And they began hauling it towards port. And the thing is that Elon Musk, several days later, I think 11 days later, put out a statement saying on X, or whatever you call it now. He said, doesn't look like we're going to be able to do this because we're going into rough, weather, and the waves are extremely high, and it probably will sink, right? We'll lose it. That was his expectations. But lo and behold, that never happened. In fact, just a couple days ago, the ship arrived on Christmas Island. There is a Santa Claus, Robert.
Not quite, but...
Well, don't say that to the millions of parents out there in the world either.
Oh, right.
So anyways, this thing stayed up enough, right, floated enough that they could get it to port. So I'm sure they're extremely happy they didn't lose it. And that can tell you a lot of stuff. And ultimately...
I was about to say, cutting into this thing, looking at the interior, why didn't it burst open and start taking on water? You can learn a lot from, disassembling this thing.
And remember, this is important too, right? Because this is how SpaceX is going to get their lunar lander, right, to function for the Artemis project. This is all part of it. And so this thing is going to land on the moon. Well, some future version of this object, the ship, is going to land on the moon. That's the hope. So they need a lot of these tests to go right relatively soon, because in some sense, the next flight of people to the moon will be Artemis 4, and that can't happen until the lander is checked out in Earth orbit, and that's Artemis 3. And Artemis 3 can't launch until a lander is available. And there are two companies that are developing these landers for the Artemis project. One is Blue Origin. The other one here is SpaceX, based on this design with the Starship that you see here in the ship part. So these have to go right if we want to get there. And I noticed a couple days ago, Jared Isaacman, the administrator for NASA, made an announcement that he thinks that 2027 we'll be able to meet that deadline for the launch of Artemis 3. But I can envision Artemis 3 is ready to go, the rocket's ready to go, the astronauts are ready to go. They're just still waiting for a lander, you see, to be launched. And they're not going to go until a lander is placed in low Earth orbit by SpaceX or Blue Origin.
There you go. I got to admit, I wish there was more competition with these upper level. I wish it was more than just Blue Origin and SpaceX. But it's a good start. At the lower levels is what I'm talking about. There's Ad Astra and all these other companies, but really at the top, heavy launch capability people, it's just those two.
And
Boeing tried.
yeah, and during the Apollo days, there was Grumman won the contract for the lunar module, and they had a lot of problems with that because there was a trade-off between too much weight and protection of the astronauts. So they had to drop a lot of weight by reducing the size of the windows to the point where you don't want to make them any smaller because you're going to impact the safety margin of landing on the moon. All these issues. You made the, if you like, the shell of the lander as thin as possible, so then you could save on weight and so on. So there was a lot of things that went into that, and they kept trying and trying. So that was delayed a lot, also.
Yeah.
So it's always I don't know why it's always the lander. So here are two projects, and it's the lander both times that's seem to be causing delays or potential delays.
Oh, come on. The lander is the hardest thing. I mean,
why can't you design that earlier? Why do you got to wait?
Now, that I'll agree with, but the lander is, especially a lunar or Martian lander, is difficult. On Earth, heck, you let it fall for a certain point till it slows down enough that it won't rip apart a parachute, and you pop a parachute and land. But you don't have any air on the moon, and you have very little on Mars. So these aren't really good options. So how do you do it? And you got to feather that propulsion system and keep it level when you're dealing with an inverted pendulum. It's a difficult process.
But couldn't we use what we did in the Apollo and then just update it and use that? You don't have to reinvent the wheel.
Now, I agree completely there. Update the electronics and push it back out there,
I mean, in some sense, if you look at what Blue Origin has proposed, it's like that. It's like a glorified lunar module, just larger to hold more people and more propellant and so on. But if you look at this for SpaceX, it's a completely different design.
Right.
And it's
reinventing the wheel.
Yeah, and it's not something they had already done 5-10 years ago. This is like novel technology that needs to be matured to the level where it's safe.
Right.
And I know one thing. I would not like to land in this thing for the first time, be the first people in it. Unless it's already landed several times on the moon and there was no issues.
Right.
So
and then again, you always got people like Buzz Aldrin, Neil Armstrong, that'll go down in a bathtub if you let them,
And that's why they're heroes, Robert. And my name is Average Joe. You see?
You got it. I'm right there with you, man.
That's the difference,
It is.
Okay, so hopefully we'll see what happens. Flight number 14 should be coming up here soon, hopefully next month or so, if all goes well. And we'll see how that works out. That ship is supposed to go in orbit. That hasn't happened yet. It's all been the suborbital flights. So we'll see how things turn out there. And unfortunately, we have to report that NASA has officially abandoned its attempt to use the Link satellite, which was, if you remember, talking about this also in the past, from the Catalyst Space Technologies company, that rushed to put up the Link satellite, and it had thrusters and 4 arms, sort of mechanical arms, that would go up to the Swift Gamma Ray Observatory, latch onto it, and help boost it into a higher orbit. This observatory, which has been produced a lot of amazing science, is ready to come back. It's in a low enough orbit. It's feeling Earth's atmosphere to the extent where it's on a decaying orbit. And they estimate it by the end of this summer, if not early fall, that it'll just come down too much so, and then it'll burn up, as it re-enters, and that'll be the end of the observatory. So there was a hope that the observatory is still functioning, still useful, that all we have to do is boost it into a higher orbit, and it could give us several more years of observations. But that's not going to happen. This was sort of put together at the last moment. It wasn't one of these things that you have to take 10 years and jump through a bunch of funding hoops and all these things to get it launched. This was something that was slapped together by this private company with the help of NASA, relatively short period of time. And because of that, do you do as good as job checking everything out? I'd say no. You just don't have the time to do the details of what you need. So there was always a risk. So it's a high payoff, but a big risk on these type of missions. So when it was launched, it wasn't shortly thereafter, they had thruster problems. And they tried to change things by uploading different software to control the thrusters. And then they had problems, I heard, with the mechanical arms as well. There was enough problems that it got down to the point where we have one reliable thruster, and NASA decided, the risk is just too great. You might collide with the observatory and all of that. We won't risk that, and therefore we'll just cancel the mission. It's supposed to now. The new mission is to go up and rendezvous with the observatory, so get nearby, just to prove that can be done. But hey, we've been doing that for decades in the space, right?
Yeah.
Agency, space industry. It's not that big of a deal, but they're not going to attach and try to boost a higher orbit. I don't know why. If they're thinking of collision, maybe it's in low Earth orbit. So even if it broke apart in a million pieces, all those pieces will rapidly come back to the Earth.
Should decay
right?
rapidly. Yeah.
It's not in a high Earth orbit. You have to worry about orbital debris for future stuff or what's up there now. So if I was NASA, if I was my decision, and given some reason I don't know about right now, why not try? Why not try?
Yeah, go for it.
You've
got everything to gain and little to lose. So I'm with you. We do have a comment that I want to mention. It's not a question, but John Porton, 8303, comments, they need to start building these satellites up in space. And that's a neat idea, and it has been proposed. Just sending up the components, the basic materials. You can send them on different missions, put it together in space, launch it off the platform.
And we've done that already. It's called the International Space Station.
Yes. Yeah.
What was that?
So we've got proof of concept there.
Yeah. What did that require? 20 some odd flights of the space shuttle, each individual piece, and bolted together when it's up there.
There you go.
So we've done that. And for very large stuff, a lot of people propose that for many years of doing just that. Right, if you're going to Mars, right, put up multiple flights to get the equipment into low Earth orbit, assemble things there, and then on to Mars. So that's
it makes sense.
It does, and it's going to happen that way, right? I mean, Starship, who knows, but that may be near the top limit of what you can actually send up with a chemical-based rocket like that. So from there on, maybe the amount of payload you can put up has to be done in multiple rocket launches. You can't do it just one single, two-stage to orbit type of stuff, right? It just won't work. The early attempts, like when people were thinking about what type of rocket should we build to get people to the moon, which ultimately led to the Saturn V with 3 stages, they were looking at scenarios like one stage to orbit type of rockets.
With the technology then, I don't think it could have been done. And obviously it wasn't, but I don't think it could have. We could pull it off now. Yeah. Because we have higher efficiency engine capability and so forth. But definitely couldn't have been done then.
No, for sure. And I think they realized that when they did the study. And that's why when they thought about the multi-stage rockets, right, like, other people had tried in the past, that was the way to go. That's the only way to lose enough mass so that you can get the rest of the rocket into space type of thing. But that was a concept people looked at, and I'm sure if it was, the technology was such, material development, so they can make things a lot, less massive than what they are today, the components that make up the rockets, all of that stuff. You get to a point where maybe you can do a single stage to orbit. So, but anyways, multi-stage right now is the way, it seems like that's the way to go. Right. If it was, if you could do, Robert, if you could do one stage orbit, wouldn't SpaceX be doing that already?
I was going to comment on that, and I'm not sure they would. I wish, my friend James, who was a rocket scientist, literally, was watching the show and could chime in. But I still think, even if you could, that it makes more sense to do it in multiple stages because you can reduce your weight, you can carry more fuel with that reduced weight, and you don't have to lug it all up there. You know, you can break off part of it and send it back to Earth while the rest of it keeps on going, you know. I think logistically it just makes a lot more sense to do it in stages, even if you did have the thrust to do it in one.
And it's really what, a cost-benefit analysis.
Yes.
Ultimately, how much does it cost per pound of payload?
There you go. And that's what you're trying to reduce.
Yeah.
Is the cost per pound to get it into orbit.
Right. That's the magic number you work with.
Mm-hmm.
Now, so anyways, this won't happen. So sometime this fall we'll hear about the Swift Observatory. You know, people will be predicting the time it will re-enter and burn up, you know, most of it probably coming through the atmosphere. So
now I do have to ask, Wayne,
yeah.
do you know if it's a controlled re-entry or is this one of the satellites that came before that agreement and treaty and it's going to land who knows where?
As far as I know, the only one in control of this satellite is Isaac Newton, if you get my drift.
Dang it.
Yeah.
Well, we may be going heads up here, folks.
But don't take that my word for it, but I think that's the case, but I'm not 100% sure. And if it is a little bit controllable, they'll try to steer it in the Pacific Ocean, right?
Oh, absolutely.
That's the largest target you want to hit on the Earth if you're bringing something back, drive it into the ocean.
Yeah.
Anyways, we'll see. And then the other thing is, how powerful are the thrusters on board? How much steering control do you have when it's re-entering? Because you got all these dynamical forces, right, from the atmosphere affecting it. Maybe you can't even steer it properly. But then again, if you aim for the Pacific, try to dump it out of orbit so that it does hit the Pacific Ocean, then maybe you'll be okay there. But I haven't heard anything about that. As far as I know, it's just coming down and Mother Nature's going to do its thing, i.e. Newton.
Yeah. And at least the Pacific is a pretty big target. So even if you miss, you're still in the Pacific Ocean.
Yeah. Yeah, I mean, that's why, like, the Mir space station that the Russians brought back, that's why that was dumped into the, the Pacific Ocean. The Skylab was different. You remember that reentry?
I do.
And
I remember a big chunk of it being brought out to Miss Universe pageant, in fact.
And that wasn't controlled either. That came down on its own. It just so happens that water covers, 74% of the planet surface area. So odds are it's going to land in water somewhere. Mm-hmm. As long as it's not your bathtub. So that landed right off Australia. In fact, some of the pieces actually landed on Australia. Mm-hmm. It didn't all land on the water. But that was uncontrolled reentry. And yes, there's supposed to be agreements amongst countries, and they don't always do it. I can give you an example of a country that launches a rocket, and part of that rocket just randomly drops on the ground somewhere. In fact, it drops one of the stage on its own people.
Yeah.
And I won't mention the country, but you probably could guess who that would be. Anyways, so there are a lot of these agreements, but do countries always oblige, or they're obliged to do it? Do they always honor that agreement? No. And you could always say, even though it might cost a little bit of money to do this, well, there was technical problems and the thing was beyond our control. Right? So there's always a note and that kind of stuff. You just never know. Yeah. Didn't mean to do that. That's all you have to say.
Yeah. I think there's an Australian band that even made a song about that. It's a mistake, You
mean the Men Down Under?
Yeah.
Anyways, so the other thing I want to update you on was the impact of the Falcon 9 upper stage that hit the moon. What was that? Way back in August the 5th. And this was the night, so this was like at 1:32 a.m. our time, and it was clear here in Grand Forks. So you were at the telescope, and you forgot about it.
I forgot about it.
You were doing your thing out there, and I was in my backyard with my 12-inch telescope Dobsonian, focused on the moon, no pun intended. Well, actually, pun intended. Looking to see if I could see a plume of material rising up and catching the sunlight where it hit near the terminator, that is the separation between the day and night side of the moon. Didn't see anything. In fact, just to make sure I wasn't doing something wrong, I had other streams that were running at the time. They were looking, they had actually larger telescopes than I had in better locations. They didn't see anything. And then over the next day or so, the reports started trickling in. Yeah, that some of the big observatories saw something. One down in Chile, for example. And then eventually South Korea, who has a lunar orbiter, took an image of an area that you could see now the appearance of a new crater. It was kind of on the like a shallow angle shot. It wasn't directly overhead, if you like, and so it was a little harder to see. But finally, NASA's Lunar Reconnaissance Orbiter flew essentially overhead of the impact area now that they knew where it was, right, from the South Korea images and so on with their stuff. And they were able to put together, a before and after images, which I show here. So on the left side, that's the before the impact, and on the right side, you can see the new beautiful crater, if you want to call it that was created by the second stage of the Falcon 9 rocket. So it definitely hit the moon. There's no doubt about it. And you can see some stuff. For example, if you look in that new crater on the right, there is like a central peak.
Mm-hmm.
Right? And you can, Robert, you know this yourself. You've done this. You could take like muddy sand or something, or mud, let's just say, and drop an object into it. And the shock wave, the rebound effect, will create naturally these central peaks. That's why a lot of these craters have it over a certain size, right?
Mm-hmm. Agreed.
And the other thing you notice, too, is the rays, as we call it, that emanate away from the crater itself on the surface of the moon are nice and bright, like they're white in color. So they expose, fresh material, fresh regolith, as the material's called, underground a bit where it hasn't been exposed to sun for billions of years, essentially. And so you can tell that it's a freshly made crater. I mean, there's no faking it or getting around. It has all the characteristics you would expect.
There you go. And yeah, but I will, the geologist in me is about to come out now. Those central peaks, a lot of people don't realize and everything, but if you put rock under the right amount of pressure and temperature, despite how solid it seems to our hands, it actually does start behaving, rock does start behaving as a fluid. And so that's why these central rebound peaks happen, and the shock waves radiating outward. This is because you've put enough pressure on it and enough heat energy added to it that it starts behaving for a little bit like a fluid. So,
and the mass of those peaks, if it's massive enough, given where you are, in this case the moon, they will collapse in on themselves, and you'll get the nice smooth bowls in the craters.
There you go.
So there must be a lot of parameters, if you like, a lot of things you have to think about, like the impact energy of the impactor, right? If there's any remnant left over from the impactor, right? And that material is going to be affected, obviously. And then some of that material will go into making the central peaks, and whether they can stand up, under their own mass in that environment and not collapse. I mean, there's a lot of things that go into that.
Yeah. As we like to say, especially in physics or chemistry, there are a lot of degrees of freedom.
Yeah, exactly.
And, that's what's going on. It's a complicated system, and we like to get simple answers, but cases like crater formation, it is not a simple answer.
Yeah, so if you do splat in a mud bath, those splats, there's a lot of physics involved there.
Oh, love it. Yes. Non-Newtonian fluids, stress, strain.
Yeah, all kinds. And the other thing, too, speaking about the moon itself, is that China, and I didn't hear the latest on this, but is prepared any day now to launch Chang'e 7 to the lunar South Pole. And in this slide, in the bottom right, you'll see a image that was taken by NASA, probably the Lunar Reconnaissance Orbiter again, of Shackleton Crater. And Shackleton Crater is essentially at the south pole of the moon. And in fact, the bottom part of the crater doesn't see daylight. The sun doesn't get high enough above the crater rim so that it can fully illuminate the bottom of this crater. So it's perpetual nighttime and darkness. Now, what's there, Robert? Is there whole creatures that live there, like vampires? Because that's where they gotta stay out of the sunlight, or what is it? You know?
Yeah, there is evidence that there may be ice in water ice in the bottom of these craters like Shackleton. There's, let's see, what is it? Hydrogen spectra and some, I think, neutron resonance imagery. Just lots of little things that say, hey, that's radar. That's behaving like water ice. Now, again, as I've kind of mentioned in other places like Titan and so forth, when we say ice, this is not what's in your deep freeze at home. Okay. This is a form of ice that you are not going to encounter in your everyday life anywhere. But we know it exists because we've got presses. We can put things under pressure. We can put things, chill them down to temperatures that aren't reasonable for Earth. And when you do that, you find that there are many different types and phases of ice. So,
and the other thing is, I mean, there's been a lot of focus on the South Pole lately of the moon, because it seems like a lot of countries want to send not only robots there, but eventually humans to explore. Mm-hmm. And if there's a big source of water, like a glacier, like you'd see in Greenland or somewhere, that's one thing you don't have to take then to the moon, is all this water for people to survive. But all these observations are showing that it's not like that at all. That this stuff, any type of H2O molecules that are there, is probably buried underneath the surface. So you're going to have to probably take a lot of that soil and just physically process it through some machine or plant that's going to squeeze or extract the water molecules out of that soil eventually.
Right.
So it's not like you're going to jam a straw down in there and try to get a drink or something, right?
But at the same time, it may be more energy efficient to do that, to go to that work, than try to lug water up there.
Yeah.
Because water's heavy stuff. It really is. It's dense for a fluid, for a liquid.
I remember way back, it's just like early 90s, the Clementine mission from the U.S. military, which was testing out a bunch of detectors and sensors. They went into orbit with their spacecraft around the moon and sent back possible evidence of water, on the South Pole, and they're even looking at for the North Pole as well. And then that evidence kind of ebbs and flows over time, depending on the spacecraft and the detector and the technology we're using. And there's nothing like they say, boots on the ground.
Oh, absolutely.
You got to get there and actually in situ, right? You got to do whatever you do. Take a shovel if you like. Dig up some of that soil and analyze it and see if there's any trace of water in that soil. And the idea is, where did that water come from? Well, the speculation is related to where did the water come from on Earth? And we went back and forth on this, and the latest was, there is evidence that some of that water probably came from comets that impacted the Earth long ago. And if it came to Earth, it also would have went to the moon. And the stuff that's exposed to the sunlight would long since evaporate away, so it would no longer exist. But if it ended up going into some of these craters that are in perpetual darkness, then it wouldn't have evaporated away. It's frozen in that state. And it could be under the ground, like we said, but we're not expecting blocks of ice like you're clearing off the ground. And then you can take a pickaxe and chop some ice off and drop it in your drink later on when you're inside the habitable module into your gin and tonic or something. It's not like that at all.
Or it may be like the water in the mantle. I mean, everybody's probably seen the headlines now about two oceans worth of water in the Earth's mantle. This isn't liquid water, folks. This is what we call hydrous minerals. The water is bound up in the mineral, not as a liquid. It's actually chemically absorbed into it. And the water on the moon, especially at the South Pole, may be in that form. You've got to chemically extract it back out. So, a lot of unknowns here, but if we can find a source of water on the moon, that's big. That's huge.
And there's 3 major countries, of course, whose attention is to go to the moon and back again for the United States, of course, but to redirect their landing sites at the South Pole because of this.
Mm-hmm.
That includes the United States with the Artemis project, it includes China, it includes Russia, and all the other countries that are kind of part of the alliance of doing this kind of stuff. So it's captured people's attention, and because of that, it's a really hostile environment. You ever see how heavily cratered the South Pole is on the moon?
Yes. But space is hostile, so
it is. And if you're in a large enough crater, the bottom of it is essentially going to be flat anyway, so that's the place you want to land.
Right.
So if you're jumping from crater to crater, that's one thing. But anyways, we'll see how all that. Of course, we need a lander, Robert, going back to that.
Yep.
We can't get there without a lander. Anyway, speaking about landers, so Chang'e 7 is sending a robot, with a rover on board and a lander and stuff to explore the region around this area, the South Pole of the moon. Now, we did have an announcement a couple of years ago, remember, of India saying, hey, we landed on the South Pole. Nobody has ever done that. And then if you actually look to see where they're landed, they weren't even near the South Pole.
Right.
So they were closer than any other country, but they weren't at the South Pole. It's almost like claiming, you land in Australia, that you're now at the South Pole of the Earth. It's almost a little bit like that in some sense. So
it's about like, landing in Saskatchewan and saying you're at the North Pole.
Yeah. Anyways, but the China's plan with this spacecraft and this mission is to land very near the South Pole. So this will be the closest to the South Pole that anyone will ever get, if it's successful, of course. We'll see what happens.
We do have a question.
Yep.
But the moon water wouldn't be under as much pressure as water bound underground on Earth, right? And the answer is no, it wouldn't have the pressure, but it would have a much lower temperature. We're talking, minus, what is it? Minus 180 Fahrenheit or something.
Yeah, it's like minus 250 at night.
Yeah.
Fahrenheit.
So, here on the moon, the issue with it being in a different phase is not pressure so much as it's cold. Without the sun shining on it, it's cold.
And Robert, if you drill down through from the moon, let's say, and you go down tens and tens of feet, and you were tracking the temperature, so the temperature would increase like it does on the Earth, right?
Yes.
As you get your radioactive decay of material, that's part of the lunar surfaces, the lunar material as well, correct?
Correct.
Yeah.
It would not be I don't think it's as pronounced a thermal gradient as it is digging into Earth. But yes, you would expect, we haven't done it to verify, but you would expect that the temperature would increase after a few inches.
Because one of the sort of hypotheses of how the moon formed was carved out by an impactor of a body about the size of Mars. Mm-hmm. But that material that they think that came off, when you're based on simulations and how this should work, because you want that material to be captured and coalesce together in Earth's orbit, ultimately form the moon. That's from the outer part of the Earth, right? That's not from deep down in the core region of the Earth itself. Isn't that true?
That is true, and we also have other evidence that backs that up. It's not just simulations, everything.
Isotopic ratio of the elements that we find on the moon.
There's that, and there's also the moment of inertia.
Oh, right. Okay.
The moon has the moment of inertia of a uniform, even closer, of a uniform body. So we know the outer layers are rock. So if it's uniform throughout, there is no real iron or metal core, which means its forming materials had to be rock.
Yeah. And
it couldn't have come from the center.
Right. And the way for people who are not as versed in physics to test that is just think of an egg. Imagine you had an egg that's raw and then one that's hard boiled. Spin them and see how they react differently when they spin. Mm-hmm. And that's a difference, a moment of inertia, given their internal structure.
Yeah, because despite what a lot of people think, the moon is rotating. It is spinning.
Yes.
Otherwise, it wouldn't show the same face towards Earth.
Right.
It would change which side was pointed toward Earth if it wasn't spinning. So it is spinning. It's just that its if you will, its spin rate matches its orbital rate.
Exactly.
And so they stay synced up.
And that's all due to gravitational tidal effects over 4.5 billion years.
There you go.
And the moon is moving away from the Earth. It's like, what, a centimeter a year or something like that?
3. But
3
yes,
centimeters
3
a year.
centimeters a year.
So about an inch a year
Mm-hmm.
And we could accurately gauge that by bouncing lasers off of the moon. We have reflectors on the
Off of
moon.
reflectors left by the Apollo missions.
Right. But of course, they
Yep.
could have been brought there by robots. See, Robert, that doesn't prove anything.
Uh-huh.
And if you had good enough cameras and see the footprints on the moon, of course, they could have been stamped by robots that had boots attached to them to fake the moon landing.
Right.
Anyways, yeah.
Anyway.
That's how all that works, you see?
There we go.
Now, the next story I want to bring up is actually evidence here of the existence of life. And we talked about this in the past. We've had, people on that we talked about early life. Where does life come from? How do you take something that's not alive at all and make it alive? And great mysteries, right, around us today that we need to solve at some point.
We know more about it than people think we do, but there's still levels of questions.
There are. And the other thing is, we always wonder, what is the earliest time in the history of the Earth that life was around? And it's amazing when you think about it. We had evidence from stromatolites and so on that showed that, life was here at least 3 to 3.5 billion years ago. That's only a billion years after Earth's first form. So
Right.
clearly life as we know it would not have survived in that very early Earth, a million years after formation. It would be extremely hot and so on, and probably a very hostile place for the beginning of life. But certainly after a billion years, or even before that, one would imagine life would have got a foothold. However that happened, we don't have the details. That doesn't mean it was some super magic power that did it and waved a wand on the Earth and there's life. It just means we don't have everything figured out yet, which means
Right.
we have work to do, right, in science. We don't know everything. We never claim we did. So
Right.
there are things we need to work on still. Anyways, this paper that was recently published suggested that there is evidence for carbon that was made by life forms that was located in India, and that the carbon is buried inside these zircons, which we've seen stories about this for many years now, and they can date that up to 3.5 billion years old.
Yeah. Now, I'm going to point out a few things. This is not saying they've carbon dated it. Carbon dating is good only to about 57 to 70,000 years ago.
What's the half-life of the carbon-13 that we use? Like 12,000 years, right?
Right.
So a few half-lives, and then it gets to the point where you can't detect it anymore.
Bingo. So this is not done via carbon dating, but zircons are neat because they are impervious to leaching in or out of either uranium or lead. And so it's the uranium lead radioactive chain that is being dated to give that 3.5 billion years. Want to make that clear because this is talking about carbon. So, they're trying to claim they carbon dated it. No, they absolutely did not. But what I'd be interested in is why they're saying this is biogenic carbon, because how did they know? How are they able to tell? I have to question that because your teeth are a mineral called apatite. You can go find apatite mineral rocks outside your door. Okay. So chemically, it's the exact same material. So how do they know this is biogenic?
Yeah, and they make the argument that it's isotopic compositions that give away evidence for that. The different isotopes. So same elements, just different isotope, different number of neutrons in the individual atoms of the material. But when you mentioned about the uranium lead dating, I actually have a number on that I can give you, and you can see it there in the abstract. So I'll put it in billions of years. So the date comes back as 3.497 plus or minus 0.005 billion years.
Yep.
The precision on that is amazing.
Yeah.
How close that is to the real is still.
Yeah.
Yeah.
I as someone who goes along with and understands radiometric dating, I'm going to sit here and say, I want to see where they get error bars that narrow.
Yeah.
Because there are still radiometric dating is accurate. do not get me wrong, but what are your assumptions about the initial ratios of uranium? Because there's more than one isotope of uranium, and they have different decay chains. Several of them lead to similar isotopes of lead, though. So I always cringe a little bit when I see those type of dating, because it leaves cracks open for people to say, "Oh, how do you know that?" That's like saying it was Thursday, in the year. Anyway, yeah.
And the other thing too is you can see in this slide on the top right you have the microscopic views of the zircon, and they date individually, and they come up and they cluster. That is, there's a grouping around that age. It's not every single one of them has that age, right? There's a spread or a dispersion in the age. They're all pretty close, but where they get this value with the uncertainty is they take where is the peak of that distribution, and they use that as a way of coming up with this number.
And the other thing is they don't just rely on uranium lead. They rely on potassium argon. They check many of these different radiometric systems. And if they're all pointing to the same place, because they're not linked, they don't have anything to do with each other. So if they're all pointing to the same age, I'm going to lay odds that it's that age.
And speaking about age, one of the interesting things was another study came out recently about sending these cubes, right, to probe the early age of the universe itself, the sort of the dark ages. So, early on when the universe sort of first formed, you have the cosmic microwave background. So there's this detailed sort of thing that occurred where the universe was completely ionized because it was so darn hot. And hot, I mean temperatures in excess of 3,000 degrees. And it doesn't matter if it's Fahrenheit or Celsius, still a large number. And nothing could form in terms of atomic atoms, like neutral atomic atoms, right? Everything was all ionized. Electrons are running around everywhere, interacting with photons that come literally from the heat of the Big Bang. And neutral atoms formed after the universe expanded enough and the temperature dropped so that energetically it was favorable for electrons to be bound up with different protons, like would create a hydrogen atom, for example. And eventually what happened, roughly about 380,000 years after the universe formed, after the Big Bang, if you like, is that the temperature dropped below a point where all of a sudden neutral atoms started forming, and that leftover heat from the Big Bang, the cosmic microwave background, could freely stream everywhere. But it was still hot enough that structures like stars and galaxies did not exist. So in that sense, that was the start of the dark ages of the universe. Right. So the universe was initially ionized, then became neutral because of that lowering of the temperature. But then when structures started forming like energetic stars, eventually black holes and quasars and all that stuff, then the universe became ionized again, and we call that reionization age or phase of the universe.
But by that time, it was so dispersed that light could still travel. So,
and the thing is that before that reionization event, you really don't have a lot of information on what was going on in the universe because there's not stuff there that was lighting up to be bright enough that we could see it, back in that early epoch of the universe. So we're always thinking of ways, how can we probe the dark ages of the universe? And this slide I'm showing here actually shows a little bit about that history. So on the top, we have the Big Bang. Let's say on the far left of this diagram, the universe is fully ionized because of the heat. Then it expands. Eventually, material combines. We call that recombination. And then it's neutralized, the universe. But then you go through this period of dark ages, however long that actually lasts, several 100 million years or whatever the number turns out to be. And then eventually structure forms, and we know now from the James Webb Space Telescope observation this structure formed much earlier than what we thought, which means this time of the dark ages is shorter in terms of overall number of years. But we're always trying to probe what was going on back in those dark ages. And one way you could do that is by looking at hydrogen. So neutral atomic hydrogen would have formed right after 380,000 years after the Big Bang. But then before stars and galaxies light up, then what was that hydrogen doing?
Right.
And in order to probe that, you need devices that are sensitive to that hydrogen, which emits. If the hydrogen atom's in our laboratory, right? If you wait long enough, that hydrogen atom is going to spit out a light, a photon, of a wavelength of about 21 centimeters, which you detect with a radio telescope. And so what this project is aimed at doing is to building these small little satellites, these CosmoCube type satellites, launching them into lunar orbit. So then when they're on the far side of the moon relative to the Earth, they're not affected by any radio interference that would disturb this 21 centimeter emission. And notice that we're detecting hydrogen, right, from very early in the history of the universe. And because the universe is expanding, those wavelengths had all been greatly redshifted.
Right.
So the mission that we pick up with our equipment is not at 21 centimeters. You have to tune it to a much longer wavelength, a much lower frequency. So the radio interference from the Earth becomes a problem. And you want to put these detectors somewhere where it's radio quiet. And right now, the easy place to get to is on the far side of the moon. So anytime that these satellites, as you see in this slide, swing behind the moon relative to the Earth, they're going to make these observations. That's kind of like the green segment of that circle that you see that represents their orbit. And then when they start coming out of the other side of the moon relative to the Earth, so then we can see it, then they can't make the observations anymore. And then when they're on their closest approach to the Earth, they're going to beam back their data. That's the X-band photons you see there from the red segment. And then they swing around and go on the other side of the moon again relative to the Earth, and then they can make observations of the early dark ages. So this is an idea that's out there that people are looking at, and we'll see if this actually flies or not. But it's a good use of these, if you like, these micro satellites, right, to do just that.
Yep. And we do have a question, but then what is the ground state of the hydrogen atom in the first place? And I'm going to go on record as saying that's a whole class we call quantum mechanics, because it is detailed by the strength of the electromagnetic force and the interaction between proton and electron and the quantum states, probability space, all of that. But, we know it takes 13.1 electron volts to ionize from ground state a hydrogen atom.
13.6.
There we go.
But the thing to remember about this is that the ground state of the hydrogen atom is actually split into two. We call it hyperfine splitting. And there's sort of an upper ground state and a slightly lower ground state in terms of energy. And that difference in energy is enough that corresponds to, when you convert it, the right conversion factor, that corresponds to a wavelength of 21.1 centimeters. The longer the wavelength.
And so that's the 21.1 centimeter line.
So what happens is, if you think of spinning like tops, which is not what atoms are like, but imagine that we're using that as an analogy. If the proton and the electron are spinning in the same direction, we call those parallel spins. The electron is in that slightly higher energy level. And what all atoms, in fact, all systems normally want to be, is in the lowest energy state. I mean, I want to be in the lowest energy state when I'm on my couch watching TV compared to jogging around the living room, you see? So all things tend to want to be in that lowest energy state. So what happens over time is that eventually the electron will drop to that lower energy state in the ground state, flip its spin, so now it's rotating in the opposite direction compared to the proton. We call that anti-parallel spins, and that's that flipping, that transition from the slightly higher energy state to the slightly lower energy state is the release of that 21.1 centimeter photon.
Yep.
Okay, that's where that comes from. Now, the probability of this occurring, if you took a single neutral atomic hydrogen atom and had it in a container and you were staring at it, on average, you'd have to wait on the order of a few million years before it would flip its spin. So when scientists first calculated that this could happen, They said, oh, there's no way we're going to detect that 21 centimeter emission from hydrogen atoms because we're going to have to wait a long period of time for it to occur. So at any given moment, what's the chance of it occurring? And what they forgot, or they didn't know at the time, was a better way of describing it, they didn't realize how abundant hydrogen is in the universe. It is the most abundant element in the cosmos. And at any given moment, there are lots of hydrogen atoms that are flipping their spin, quote unquote, releasing 21 centimeter photons. And it's easy to see that emission with the telescope tuned with the right frequency. You see it all over the place.
There we go.
In fact, Robert, for those students that are in my introductory astronomy class, we have a lab, a radio telescope that's designed to detect the 21 centimeter emission from hydrogen that's in the spiral galaxy, our Milky Way galaxy. And so with just a couple $100, you can easily put together an instrument that actually can detect that stuff. That's how easy it is to detect if you know what you're looking for.
There you go. You just, again, you got to put it together, know what you're looking for, and build an instrument that will see, is it there? You make a prediction, you test that prediction. There it is.
There it is.
Yeah.
Now, of course, you too can get involved in all this kind of stuff, and one way to do that is come to the great University of North Dakota. You know, we have a STEM building, and every day I swear it's getting taller and taller and taller.
I don't think it's getting taller, but it's getting deeper.
To me, everything gets taller because I'm short.
Oh, fair.
The metal expands as they cool down the temperature, you know, as we're heading into, don't say it too loud, heading into winter, you know.
Yeah.
And then with the heat during the day, it expands, and at night it contracts, you know, that kind of stuff.
Yeah.
But seriously, the STEM building is starting to come together a lot now. So they're working like crazy on it, trying to get as much done probably before the winter does sit in.
Yeah.
Which is, you know, the harsh part of it comes usually in December sometime, you know, after U.S. Thanksgiving. We start getting into really cold temperatures, so we'll see how it goes. But there's a lot of stuff happening here on campus. So if you're interested in higher education and you're trying to figure out where to go, please consider UND, the University of North Dakota. Lots of stuff, both online and on campus, right? So there are lots of programs that we're involved in from all over the place, not just the STEM fields, but from arts and everywhere else. So,
and semester's just starting, so now's a great time to visit. You get to see the campus with people moving around. Yeah, it's a nice place.
And it's still really warm out, so you get to enjoy that. You can walk around in shorts and not have to worry about winter jackets and things of that nature. Now, of course, we always leave you with a quote at the end of our podcast. But before I give you today's quote, it was actually relatively short, but it's about a subject we talked a lot about today. Our next podcast will be a week from now. So that, believe it or not, Robert, is going to be September the 1st.
Woohoo!
So we'll soon, Christmas will soon be here. So remember, I'm your old buddy. And if you're thinking about Christmas shopping anytime soon, I do have a list I can give you when you're ready.
Oh, okay. Oh. Notice my beard's getting white enough. So not long enough, but wide enough.
So the quote is from one of your favorite authors, Robert, Arthur C. Clarke.
Arthur Clarke, brilliant man, good writer, love his stories.
And here's the quote. The moon is the first milestone on the road to the stars.
Oh, absolutely.
And
nice one.
Yeah, and that's exactly what we're using as a jump-off point to explore not only the rest of the solar system, but hopefully in the future, the cosmos.
There we go.
So if you
get it done.
Exactly. If you like this podcast, don't forget to give us that thumbs up. Help us with our motivation, right, Robert?
That's it. Make us feel like we're not wasting our time.
Yeah. Subscribe if you haven't subscribed, and we will see you 1 week from today.
See you next week, folks.